In today's video, we're going to be talking about the Intermediate Value Theorem, which can also be just written as IVT for short, because this is a long title for a subject in your textbook. So the idea behind the Intermediate Value Theorem is if f of x, some function, is continuous along the open interval. We learned about the open interval in my last lesson. If you don't know what that is, check out my past videos. And L, some arbitrary number L, is a number between a, b, this open interval. There exists a value c, denoted as c, where f of c is equal to L. So while this definition is a bit wordy, it's not too hard to understand. This just sounds fancier for your definitions. Essentially what it's saying is if you have some function that is continuous across a set domain, such as -5 to 7 or something like that, it could be any two arbitrary numbers along the x-axis, there is a number L where if we plug in a certain number, we get L. Using a visual may help one understand this a little better. So this is going to be our xy plane, and we have this function. It looks something like that. Now this function is continuous across the entire domain, so we don't have to worry about it being continuous across an open or closed interval. And say down here is A, and over here is B. This is our interval that we have this function in between. There and there. And let's also say that this is L. This is whatever our L number is that we're looking for. What it is saying is that there is a number along A and B known as C, which could just be some constant value, that yields a y value equal to L, or if you plug it into the function, you'll get L. So while this theory is very simple, we can use it in a few cases to help us solve limit problems. But along with the intermediate value theorem is the root location theorem. So I'm going to move this graph over here and write the root location theorem over here and draw a new graph. I rewrote the definition over here, and I do want to make one slight correction. Whenever I said between A and B, I mean f of A and f of B because L is along the function. So whenever we have A and B across our interval, I mean the function value if you plug in A and the function value when you plug in B, and L is between that. So I have this entire definition rewritten here so we can reference it later. So now that we know what the intermediate value theorem is, I want to talk about something that's basically a slightly more specific version of it known as the root location theorem, which also can just be written as RLT for short because these are long theorem names, man. I don't want to rewrite these over and over. And by the way, this is IVT, which I'll just write here. The root location theorem states that if f is continuous along the closed interval, unlike the open interval from earlier, the closed interval AB, and remember, the closed interval is just represented by brackets instead of parentheses, and f of A, in other words, if you plug in A into the function, and f of b have opposite signs, then there exists a value or number, also known as c, where f of c is equal to 0. Now, why specifically 0? Well, when we're talking about roots along a graph, the root usually means the x-axis, in other words, an x-intercept, meaning that the function crosses the x-plane or at least touches it. Once again, this is a really long and wordy definition that nobody likes to read out over and over, so we're going to explain it with a visual once again. Here we have an xy plane that looks something like this, and we have this function that goes up like that and down like that, and it's continuous across the entire xy plane. And here we have our closed interval, and this is A, and our closed interval, which is B, over here. That spans this area here, denoted by these slashed lines. And if f of A, which is down here, in other words, what the function equals when you plug in A to it, and f of B, which is up here, have opposite signs, in other words, f of A down here is negative. It's below the y-axis, so this is a negative y. And f of B has a positive. In other words, it's not negative, it's positive, which is the opposite of f of A. All that means is that there exists a value c, where if we were to plug in c to our function, we would get 0, in other words, a root. And this is pretty easy to see visually, as if we have the function as at a negative point and the function at a positive point, it has to cross the x-axis at some point, which is the value c, where x is equal to 0. That's what this whole theory states. It's very wordy for a very simple thing. We're going to do a couple example problems using these theorems, so unfortunately I'm going to have to erase all my hard work. I'm going to put a screenshot of this up in the top left so that way you can reference it, because as much as I'd like to have these up, I need more room. In our first example, we have f of x being equal to x squared plus x minus 6.3. And we want to prove that f of x has a root. But not just anywhere. It has a root along the closed interval 1, 4. And remember, a closed interval includes the endpoints, which is represented with brackets. So how might we go about solving this problem? Well, first we know that we're looking for a root, which means we're going to need to use the root location theorem. The first thing we need to prove in order to use the root location theorem is if this is continuous along the closed interval. And what's nice about this function here is that it's a polynomial, and polynomials are continuous everywhere. It's a property of continuous function. I talked about that in this video. So we know this function is at least continuous, but now we need to check and see if this function crosses the x-axis. And in order to do that, we may as well check the endpoints 1 and 4. So for f of 1, this is equal to 1 squared plus 1 minus 6.3, which is equal to negative 4.3. For f of 4, remember these are just our endpoints over here on our closed interval, we have 4 squared plus 4 minus 6.3, and that is equal to 13.7. And you may notice that we have opposite signs here. Negative 4.3 is less than 0, 13.7 is greater than 0. And in order for this to happen, that means this function, x squared plus x minus 6.3, had to cross the x-axis at some point in this interval. So we just proved that yes, this in fact has a root within the closed interval 1 to 4. We don't have to find that root, we just were asked to prove if it exists in the first place. Let's do one more example so you really get the hang of this. In our second example, we want to prove that cosine of x equals 2x has a solution or a root on the closed interval 0 to pi over 2. So just like last time, we need to use the root location theorem to see if this problem has a root along this closed interval. First, we need to prove that this is a continuous function. And in its current state, it's not really a function. We want something to equal something else, and neither one of these happen to be f of x. So let's subtract 2x from this side. So now we have cosine of x minus 2x is equal to 0. So is this function continuous? Well, we do know that trig functions are always continuous, and this is also always continuous since it's just a scaled up version of the x function. Combining these two does not change the fact that this function is continuous. So yes, this function is continuous. So now, just like last time, we need to prove that this at some point crosses the x-axis to prove that there is a root within this closed interval. So let's plug in these two endpoints to our function. So let's plug in f of 0. That is cosine of 0 minus 2 times 0. Cosine of 0 is 1. 2 times 0 is just 0, so this is equal to 1. Let's do f of pi over 2 now. F of pi over 2 is equal to cosine of pi over 2 minus 2 times pi over 2. Now cosine pi over 2, if you remember your unit circle, is equal to 0. Pi over 2 is similar to the 90-degree angle like this, and your cosine is whatever your x value is. Because cosine is not going out in either direction that way or that way, it's equal to 0. So this is just 0. So this is 0 minus, and 2 times pi over 2 is just pi. Therefore, this is equal to negative pi. And you may notice that this is a positive number, and this is a negative number. So because we have one positive number and one negative number, this function had to cross the x-axis at some point. So yes, there is a solution to this problem where cosine of x equals 2x eventually equals 0. And we proved that using the root location theorem, which is based off of the intermediate value theorem. I hope this video helped you out today. Consider subscribing if you'd like more Calculus 1 lessons, along with more math lessons to come in the future. If you want to watch more Calc 1 videos, check out this playlist with every single Calc 1 lesson in case this isn't the subject you were looking for. I'll see you guys in the next video.